Hello, everyone. Um, begins the material on vapor-liquid equilibrium. So a lot of times you find in thermodynamics, you want to calculate changes in the internal energy, the enthalpy, Gibbs free energy, or the entropy, etc., etc. And we actually have equations that you can derive, not in this course, but some of my older videos, I derived these equations where you can express small changes in entropy, for instance. I'm going to do this twice for two different definitions of this. This specific enthalpy over a specific heat capacity over temperature, dt, plus, for instance, dp, dv at dp, dt, dt at constant v times dv, for instance, small change in volume. Or, it can look at the change of entropy as it relates to the various specific heat capacities, and then changes in these other properties. And similarly for internal energy, we could have CV d temperature plus T times del pressure, del temperature at constant V minus P times dV. So, and lastly for enthalpy, we'll just to drive the point home, CP. So we're very familiar with how internal energy and specific heat capacity and temperature changes relate to each other, but they also depend on what's happening with your material. And you'll see in all of these cases, the point that I'm trying to make here is that on this right-hand side of all of these equations, you see three variables constantly show up: temperature, volume, specific volume, and pressure, over and over and over. So we need to have some sort of relationship between temperature, volume, and pressure. And the first of those, of course, is the one you're all familiar with, the ideal gas law. So P V underbar equals RT, and recall that V underbar is defined as V divided by the number of moles, so the specific molar volume. But here's the problem. By definition, by name, ideal gas is not real. Just like relationships, an ideal relationship is, not a real relationship. Or, an ideal vacation is not a real vacation. Or an ideal perfect, now we're in social distancing, it's not real, because it's only at 80-90% people actually adhering to the rule for that, but it's still having an impact. So there are many ways to account for real behavior. And that's the focus of what we're going to be doing now. There are some of the big ways, and this is where we've even used in like one problem, but really in biological thermodynamics, you're not going to be consulting steam tables ad nauseum. But we could be tabulated from data in a table. From a table. So why do we have tables for steam? I mean, water and steam are everywhere and we're used all the time. Don't you think we'd have a better equation for it? Well, not really. Water is a peculiar material. We have graphical data where you just make a bunch of diagrams. Diagrams that you get data from. I really think there's probably an incredible amount of opportunity to use AI and neural networks to learn all this data, and then you can just have a neural network function give you every thermodynamic variable you could ever need. But that's for a different course. If anybody's interested in that course, you can take my quantitative systems biology, where we do get into a little bit of AI, neural networks, machine learning. Fun stuff. Okay, back to the main material here. What we use for a lot of these thermodynamic relations are EOSs, which stands for equation of state. So the ideal gas law is an example equation of state. Another one that we're going to study is the van der Waals equation of state. And this is in a subcategory of general cubic equation of state. And we'll describe what cubic equations of state mean in a moment. So I'm going to take the pause on this video here and then make another video for van der Waals equation.